Hey guys, okay, so today we're going to talk about inverses. This is going to be a really quick rundown of all the little ins and outs that you might need to know. This is something that you did in Algebra 2, so a little bit of this is going to seem familiar, but what I want to talk about first of all is some different ways to think about what an inverse is. Most of you probably remember it as just switching your x and y, which is extremely accurate when you switch x with y. And that could be done several ways, like somebody could give you points and perhaps you just take those points and literally just, flip their spots. Just make sure not to change any signs or do something weird with it. Just literally swap them out, okay? You might also be given a graph where you could take a point and flip it and do that, or an equation where you could take your equation and flip your x and y. So most people remember that definition pretty well. Another way to think about an inverse is that graphically what you are doing is you are reflecting across the line y equals x. Graphically, okay. And so if you don't remember the line y equals x, that would be just the parent function for line. So that's going to be that diagonal that runs right through the middle there. And so we'll do an example of that just to practice that. And then the third way I want to talk about inverses is by one of the definitions using composition of functions. So there is a definition. This is going to help you prove if two things are inverses, or basically try to decide maybe if two equations are inverses. And that definition says that f and g, I'm going to say f of x and g of x, are inverses in, I can't spell, are inverses. I'm going to put if and only if f of g of x is equal to g. I'm mixing my notation. Give me just a second to undo that little mark, guys. Sorry about that. I want to be consistent with my definition. G of f of x, which is equal to x. So this is one way to write out compositions. Of course, this is the same thing as if I did write it this way. These are synonymous, okay? And what we're saying here is if we take one function and plug it into the other one and we do the math to simplify, we should get an x. And then we need to do that the other way to check it as well. So let's do an example of all three of these really fast. So let's do it with a graph first, okay? So let's say that I have a sketch, maybe it's something like this, and I'm asked to find the inverse of that, okay? So one of the ways you could do it is you could actually just like find a point on this graph. So maybe if you had a scale, this would be the point 0, 2. This looks kind of like the point maybe -3, 0. And this would be your original F graph. But we could find several points on the graph that we thought were pretty good. And we would write out the x, y. Then we could take those x and y's. So like 0, 2, and then the other one I have is -3, 0. And we could swap the x with the y. So that would be 2, 0, and then 0, -3. And what that means is that these points are going to lie on the inverse graph of this. So 2, 0, 0, -3. And then we would make that, we would do that with a few more points because right now it's hard to tell sort of what would happen. But I know it's going to look something like this, and I'll explain why in just a second. And the reason I know the graph's going to look a little bit like that, if we were to pick a few more points, is because of the other definition that I wrote up there that says it's a graphical reflection across the line y equals x. So if I sketch the line y equals x, this is that parent function, the diagonal I mentioned. If I sketch this in, then what should happen is you should see like a mirror image, right? So it would be as if I could fold my paper on this line, on this black line. The blue and the green would match up. That's a way to verify or check for inverses, but that's what that relationship is. So there's swapping x and y, there's checking graphically. We could also do algebra to check something out. So like if we were asked to maybe find the inverse of the equation 2 times x minus 3 be, let's say, cubed plus 1. And if somebody says, all right, find the inverse of that. Well, step 1 is you're going to switch out the x and the y. And if you're saying to yourself, well, there's not a y, yes, there is, sillies, because remember, f of x is just the same thing as y. So this is the original equation. I'm going to take x and y and literally flip-flop them so that it's x over here and y over here. Now the goal would be to isolate y. So I'm just going to do a little bit of algebra to get y by itself. So y is kind of trapped in these parentheses. So let's start by subtracting the 1. After we do that, hopefully you're seeing the next number that would be good to get rid of is the 2 in the front. And that 2 is being multiplied. So let's divide both sides by 2 just to get rid of it. Now, I've got the y trapped inside of a function that's cubed. So how do I undo the cubed? Well, I take the cubed root of both sides. It's just like if that was a squared, most of you know to take the square root of both sides. I'm going to take the cube root of both sides, okay? And when I do that, what happens is that cube root and that cube just cancel each other out. They're actually inverse operations of each other. Oh, how ironic. How ironic. So those are going to cancel, and it's just going to leave behind y minus 3 equals, just like this. And then last step, to isolate the y as well, add the 3 over to the other side. So I'm going to come up over here because I'm running out of room. So we'll have the cubed root of x minus 1 over 2 plus 3 equals y. Now when you get your answer, it's nice to denote that you have just found the inverse. So the symbol for that is to put a -1 on that y. You might even want to get fancier and go back and rewrite that as f -1 of x using function notation and not write y. We're big kids now, so it's okay to use function notation. But that would be the inverse of the other. And so the last thing would be, of course, to use that definition I showed you to test if two things were inverses of each other. So basically that's what we're going to try to do. Check to see if f and g are inverses. Okay, so I need to make up something and we'll see if it works out or not. So let's do maybe like 2x minus 5 here. And then what we'll do over here is maybe like 1/2 x plus 5. And let's see what happens. Okay, so if I want to see if these two are inverses, what I'm going to do is that definition, which says to do f of g of x, and we want to see if that's going to simplify to the variable x. So remember, when you're doing a composition, you work inside to out. So I need to take g and plug it into f. So all of this is getting plugged into the spot in f. Okay, so if I'm doing this kind of math, then what I would do first is maybe distribute my 2. So I would have x plus 10 minus 5, and that would become x plus 5. And there is no simplifying that beyond what I've just done. So do we think they're inverses? I say no, because guess what? It would have just reduced to the letter x if it was an actual inverse of the other. And then if that had happened, you would want to do it the other way as well. Like you would want to check g of f of x as well, just to make sure, and plug it in the other way, and your wish and hope and dream is that it also would reduce to an x. But this one didn't work this way. It probably won't work the other way, so it's definitely not an inverse. Very last thing, because I know this is longer than I thought it would be for Cliff Notes. One thing I need to say, not every function has an inverse function, okay? Not every function has an inverse function. The only functions that have inverse functions are functions that are said to be one-to-one. And what one-to-one means, I'm going to write sort of the graphical way to check, but it means that your function is going to pass both the vertical line test, which you might remember proves that something is a function, but it's also going to pass a horizontal line test. So we haven't done this before, but you're going to want to check a graph. So if I were to sketch something like perhaps this, okay, which is similar to the one we did a second ago. This is, of course, a function, because if I draw vertical lines, I only hit the graph in one spot. But if I were to draw horizontal lines, we want to see if we also only hit the graph in one spot. Now, here we do. I hit it once. Here's another horizontal. Here's another horizontal. But right in here somewhere, we're going to break that rule, and this passes the graph like too many times. So this is not going to have an inverse function. Okay? So you definitely want to check that. Now, the official formal definition of a one-to-one function is not what I just drew, but a one-to-one function is every input has exactly one output and every output has exactly one input, meaning each x has a specific y, but the y's also only have one specific x, okay? And some of you, that's going to make sense now that you've seen the picture. But just make sure that you check that before you do it. So anything that's going to break the horizontal line test is not going to have an inverse. And if you know that, it's very powerful, because if someone gives you something like 3x squared plus the absolute value of x minus 1, I don't know what this looks like. You don't know what this looks like. But I know that this is probably not going to have an inverse function, because if you think of this parent function, this would be a parabola, fails the horizontal line test. This would be the graph of absolute value, which also fails the horizontal line test. And then this is a constant, and the graph of a constant is literally a horizontal line. So this term is even, this term is even, and this term is even. So if you are an even function, you are having y-axis symmetry, and you are going to fail the horizontal line test. Therefore, no inverse function for you. So hopefully a little bit of that made sense, and that will get you guys started on doing a little bit of practice with inverses. Thanks.